Right, so I'm talking about controlling elliptic PDE and application to inverse problems. There will be 3 parts in the talk. So first I will talk about a certain motivating example of an inverse problem for elliptic PDE, namely the Calderon problem, which is one of the most famous problems of this type. And after this motivation, I'll discuss this idea of controlling solutions to elliptic PDE in the framework of the roon approximation property. And I'll explain some recent applications in the field of inverse problems of these approximate controllability type things. And the last part will be about fractional equations involving the fractional operation. And it turns out that these control properties for fractional equations are much more powerful than those for the classical equations, and one can do more in that setting. Okay. So the Calderon problem goes back to the 1920s. In seismic imaging applications, people were interested in figuring out if there are oil deposits in certain parts below the Earth's surface. And there are several methods for trying to find oil inside the Earth. And one of these is somehow electrical resistivity imaging, where the idea is that you have a field set up, you put electrodes on the surface of the Earth, and then you inject some currents in these electrodes, and then there will be current flowing through the subsurface, and then it's coming back to the surface, and then you're going to measure the corresponding voltages. And from these electrical measurements of these currents which have gone through the subsurface, you want to determine if there's an oil deposit or not. And in mathematics, this problem is called the Calderon problem because Alberto Calderon gave a very nice mathematical formulation of this problem, and he solved the linearized version of it. And so the mathematical model would be the conductivity equation. So we have a domain omega, which is the medium that we want to study. It could be the Earth, for instance. For mathematically, it will be a bounded Lipschitz domain in Rn. And there's a positive scalar function gamma in omega, and this will be the electrical conductivity at each point inside the Earth. And you have these electrodes on the surface, which is the boundary of omega, and then you can impose a voltage on the boundary, which will be a Dirichlet condition for this elliptic equation, so u equal to f on the boundary. And then the voltage u is going to solve this conductivity equation, divergence of gamma x nabla u equal to 0 in omega. And the idea is that you use your electrodes on the boundary to put many different Dirichlet data f, and then you always measure the corresponding currents, which are given by this Neumann data gamma times the normal derivative of the solution u at the boundary. And you repeat this for many Dirichlet data f, always measure the corresponding currents. And in this way, in a mathematical idealization, your boundary measurements will be given by the Dirichlet to Neumann map lambda gamma, which can be thought of as a map from, let's say, Sobolev space h1/2 of the boundary into h-1/2, which takes the Dirichlet data f into the Neumann data. So this map encodes the electrical measurements that you are doing at the boundary. The inverse problem would be if you know these electrical boundary measurements given by this map lambda gamma, you want to determine gamma. Okay, so this is the problem. And this is not just important because of its connection to electrical imaging. It turns out to be a model case for many inverse problems for elliptic equations like Schrödinger or Maxwell or stationary linearized elasticity or Navier-Stokes equations. And besides electrical imaging, it's also related to optical or acoustic imaging and inverse scattering problems, and even this business of building invisibility cloaks, where you try to in Harry Potter style, you want to build a cloak so that people cannot see inside. So this would be kind of a counterexample to Calderon type inverse problem. So all of these connections are a reason why this has been a central problem in the theory of inverse problems. So let's see, somehow mention a few results that are known. So these are uniqueness results saying that knowing the boundary measurement map lambda gamma allows you to determine the conductivity gamma inside at least uniquely. So there are differing results depending on the dimension. In dimension 3 and higher, the first somehow big result is due to Sylvester and Ullmann, who showed that if gamma is a C2 conductivity, you can determine it from boundary measurements. And one thing that has been of interest is to reduce the regularity. And nowadays, the result is known for ellipsis conductivities by Haberman, Tataro, and Caro Rogers, and also for conductivities in the Sobolev space W1n, at least in low dimension 3 and 4. And some people conjecture this would be an optimal result in a certain sense. In 2 dimension, the C2 result was given by Nachman in 96, and there is a kind of fairly sharp result for bounded measurable conductivities due to Astala and Päivärinta. And it turns out that all of these results, they have connections to Karleman estimates. These are exponentially weighted estimates, which are also used extensively in control theory and probably familiar to most people in the audience. And also the unique continuation principle, which is the statement that if a solution U of an elliptic PD vanishes in some small ball, then it has to vanish in the whole domain. Okay, and let me very quickly tell a little bit more what kind of mathematics goes into these results. So these results use solutions which of the conductivity equation which look like harmonic exponentials e to the rho dot x, where rho is a complex vector satisfying a condition so that this is harmonic. So the C2 result, one of the key ingredients is L2 based Karleman estimate. And if you go to lower regularity, you have to use more advanced bases. In the ellipsis case, people use so-called Bourgain spaces. These are not traditional Sobolev spaces, but they are function spaces which are adapted to the equation and some averaging arguments. And to go to W1n, you need to combine that with LP-based Karleman estimates. And in 2D, you have different methods. There's D-bar scattering theory and the use of quasi-conformal mappings. Okay, so these things are known, and let me describe a variation of this problem which will be of interest for us. So this is the local data problem. So this is the setting where you don't have electrodes on the whole boundary, but you only have them on some subset of the boundary, this red set gamma here. So you are only making measurements on part of the boundary. So mathematically, this means that you are measuring the current lambda gamma f on this small set gamma for any Dirichlet data which is supported in the same set gamma. So you're only making measurements on this possibly very small set. And so the uniqueness is known for an arbitrary open set gamma of the boundary in 2 dimensions. This is due to Imanovilo, Ullmann, and Yamamoto. In 3 and higher dimensions, there are only partial results by Koenig and myself, building on earlier work by Koenig, Sjösten, Ullmann, and Isakov. So to conclude this motivation, so let me just mention some open questions that still remain regarding the Calderon problem. So there's this local data problem in dimension 3 and higher. If you fix an arbitrary open subset gamma of the boundary, possibly very small, you want to find the conductivity gamma if you only make measurements on this subset gamma, capital gamma of the boundary. Another open problem is to instead of looking at scalar conductivity coefficients is to determine a matrix coefficient. So determine a smooth matrix A up to gauge from measurements for this equation divergence of AX W equal to 0. So now this coefficient here is a matrix instead of a scalar function. So that's a big open question. And related to this optimal regularity, one could ask for counterexamples in dimension 3 and higher. Can you find two Hölder continuous conductivities so that they have exactly the same boundary measurements, but they are not identically the same? So these questions remain open. Are there any questions at this point?
No, thank you.
Okay, thanks very much. So this was the motivation part. So let's now go to the business of controlling solutions and seeing what one can do with this method, for instance, in the Calderon problem. So at least in the context of inverse problems, this controlling solutions is often called the Runge approximation property. And this comes from the classical theorem of Runge in complex analysis, coming from, I think, 1885 or something like that. So this theorem is saying that if you have an analytic function in a simply connected domain U in the plane, then you can approximate that analytic function uniformly on compact subsets by complex polynomials. So one can kind of think of this theorem more in PDE terms. Analytic functions are solutions of the Cauchy-Riemann equation d bar u equal to 0. So this Runge's theorem is telling you that if you have a solution of d bar u equal to 0 in some subdomain capital U, then you can find solutions of the same equation in the whole complex plane, global analytic functions, which approximate the original function in the subdomain capital U. So you can state a similar, somehow general Runge property for some equation Pu equal to 0. This could be a conductivity equation, for instance, this Pu equal to 0. So you have the following setup. So you have two domains in Rn, a smaller domain U and a bigger domain omega. And the Runge property is saying that if you give any solution of the PDE, Pu equal to 0 in the subdomain U, then you can approximate that solution in U by global solutions, solutions in omega. So that would be the kind of extension of this Runge's theorem for a more general PDE. And this is valid, for example, for the conductivity equation Pu equals divergence of gamma W, if this gamma is a positive Lipschitz continuous coefficient. And the reason why you need Lipschitz continuous in dimension 3 and higher at least is that this approximation property can be proved by duality from the unique continuation principle. So this is an observation made by Lux and Malgrange in 1956. So if you have a unique continuation principle for your PDE, then you also have some approximation property. And this is of course similar to, for instance, the Hilbert uniqueness method in control theory, where some kind of observability inequality, which is kind of a uniqueness statement, implies a controllability property. Okay, so let me state the precise version of this Runge approximation. So here's a simple example of such a result. So if again you have two domains U and omega, U is a smaller one, and let's assume they have Lipschitz boundary, and there's a small topological assumption. The complement omega minus U bar has to be connected. And now you can also put an open subset gamma of the boundary, so this red set here. And the result says that if you have a solution V, which is in the Sobolev space H1 of U of the equation Pu equal to 0 in capital U, then for any epsilon, there exists a Dirichlet data F, which can be assumed to be smooth and compact supported in gamma. So it's going to be 0 on a large part of the boundary, and the support is going to be confined in gamma. So that the global solution of PU epsilon equal to 0 in omega with this Dirichlet data F is very close to this original profile V in U. So one can think of this boundary function F as a boundary control. So you have a profile V inside U, and then you want to find a global solution in omega, which approximates this profile V inside U. And you can do that by some boundary control F, which only lives on gamma. And it's a fact that this profile V that you can approximate in U, it actually has to be a solution of the equation. It's very easy to see that if you have a limit of global solutions, then that limit also has to be a solution. And this is a kind of a restriction of classical second order PDE. And this is going to be different in the fractional case. Okay, but anyway, so we can, at least to some extent, we can control solutions in subdomains by using some boundary controls. So what can one do with this idea, for instance, in the Calderon problem? So here's one application of the Runge approximation property. This is sometimes called localized potentials. So you have the following geometric setup. Again, you have a domain omega, and you have two open sets U0 and U1. And you assume that they are disjoint. And there's, again, some topological condition related to the complement. But maybe it's easier just to look at the picture. So here you have a small blue set U1 and this green set U0, which is supposed to be large. And the result is saying that you can always find global solutions of your equation PUJ equal to 0, so that in the big green set U0, this solution is almost like 0. So it's going to be very small in this big green set. And in the blue set U1, it's going to be very large. It's going to be close to the constant J, where J is going to infinity. And you can confine the support of the Dirichlet data to live in this set gamma. So these are called localized potentials. So their energy somehow concentrates in this blue set U1, and they are almost like 0 in large subsets of the domain. And how do you prove this? It's very easy. So now you take the subdomain of omega, which is the union of U0 and U1. And now because these two sets are disjoint, then you can take a solution of the PDE, which is constant 0 in U0, and which is a big constant J in U1. So this is a solution of the PDE in the union of U0 and U1. And then you just apply this Runge approximation to get the global solutions in omega that approximate these constants in these subdomains. Okay, so just to recap, by using the Runge approximation, you can produce solutions which are almost 0 in a very large set and whose energy somehow concentrates in some region of interest U1. So you could think that you might be able to use these solutions to get some information from the interior. But there's a catch. So you have the complement of U0 union U1, so this small set here, and you actually don't have much control of this solution in this small set. So it could be very bad or very, very large in this complement. But still, you can use these in inverse problems, for instance, in the Calderon problem, if somehow you already happen to know the conductivity coefficient in this set where you cannot control the solution. For instance, if you a priori know the conductivity near the boundary, or it turns out also if the conductivity is real analytic or piecewise analytic, then that's also fine. So in this way, you can use this approximate controllability results to recover a piecewise analytic conductivity from boundary measurements. You can solve the local data problem under the additional assumption that you a priori know the conductivity gamma in the neighborhood of the boundary. And also you can determine shapes of obstacles which are buried inside the domain. So these kinds of things you can do. But and this is quite classical, but so let me discuss some recent applications of this approximate controllability in inverse problems. So I'll very quickly with one slide describe each of these, at least the first three. And I don't expect that you can follow what these applications are about, but I try to give you some flavor of what kind of controllability results are being used. So there's quantitative Runge approximation. Then there's the anisotropic Calderon problem for matrix conductivity and some monotonicity methods. And then fractional equations, and these I will discuss in detail in the third part of the talk. Okay, so let's go to this quantitative Runge. So again, we have this basic setup. We have a subdomain U and a bigger domain omega, and we have a solution of a PDE in the subdomain U. We call it V, and we want to, given an epsilon, we want to find a solution U epsilon, a global solution of the PDE in omega, so that within U it approximates your profile V up to epsilon accuracy, for instance, in the L2 norm. And of course, you can have many solutions U epsilon like this, and you would like to have the one which has minimal energy in some sense, so that the H1 omega norm of U epsilon is as small as possible. So this norm here you could call the cost of approximation. And it turns out that it seems in this context of the Runge approximation provided for elliptic PDE, this quantitative result, we did not find it in the literature, although similar results were known in the control theory community. And we actually used some work of Rob Biano in the 1990s and ideas there to prove this result. So the result with Ryland is telling you that okay, if so there's three possibilities. If your profile V actually extends to a global solution, then of course you can take U epsilon equal to V here, and you have perfect approximation. So the cost of approximation is bounded by 1 if you have a global solution. But then if you have a function V which is a solution in some neighborhood of U bar, but not a solution does not extend to a solution in omega, then the cost of approximation is polynomial in 1 over epsilon. And the worst case, if you have a solution in U which does not extend into a solution to a neighborhood of U bar, then the cost of approximation is exponential in 1 over epsilon. And the proof of this kind of result, again, you use duality and unique continuation, but now you have to use a quantitative version of the unique continuation principle, which are known. And this kind of approximation is also optimal. And there's a recent paper with Koch and Ryland where we study this optimality and this cost of approximation business in a kind of fairly general setup. Okay. So the second recent application is related to the anisotropic Calderon problem. So it's a classical result of Lassas and Ullmann, and we gave recently with Lassas and Limaten a new proof of this result. So this is in a geometric setting. If MG is a compact Riemannian manifold with boundary, you want to recover a real analytic metric G. You can think of this G as kind of a matrix conductivity A of X, if you want, up to gauge from the Dirichlet-Neumann map. And so we give a new proof of this result and somehow give a new method, which we call the Poisson embedding. And the idea is that, okay, you can do measurements on the boundary of your domain, but you don't know what is inside. And in this geometric setting, you don't even know the topology of your domain. There might be holes or whatever. So somehow you need to identify the points in the inside with something that exists on the boundary, because the boundary is the thing we know and where we can make measurements. So what we actually do is we identify points in the interior by Poisson kernels, somehow correspond to those points. And Poisson kernels are functions on the boundary. So they live in the set where you can do measurements. And I'll only mention that the proof of this result is also heavily based on Runge approximation. So it uses basically two facts. So the first fact is that harmonic functions separate points. So if you have two distinct points in your domain, then you can find a solution of the PDE which takes different values at those 2 points. So this is a simple property, but this can be proved by Runge approximation. And also the fact that you can prescribe Taylor expansions of solutions of PDEs up to some natural constraints given by the PDE. So this is also something that you can get from this approximate controllability. Okay. And the third recent application is related to some shape detection methods. So this might be a little bit difficult to read if you're not familiar with this, but maybe let me just say that now instead of the conductivity equation, which is a positive equation, so the Dirichlet eigenvalues of the conductivity operator are positive. So you work with the Helmholtz equation, Laplacian plus k squared times some q. Q would be the index of refraction of or kind of a sound speed, for instance, in omega. And the idea is this equation is not positive anymore. So it can have negative eigenvalues. And also 0 could be eigenvalue. So you might have finite dimensional kernels for your Dirichlet problem. And so earlier people had developed shape detection methods based on monotonicity tests, but they only work for these positive equations. And we extended this to the Helmholtz equation or other imaging problems which have a positive frequency. And the point is that the proof uses, again, Runge approximation property, but now in the sense that you can put finitely many constraints on the Dirichlet data, and you can still have these solutions which concentrate the energy on some subdomains. So in addition to that, the Dirichlet data is supported in some small set gamma on the boundary. You can require that this Dirichlet data is orthogonal to finitely many fixed functions, and then you can still have these localized potential solutions. So that's maybe somehow the kind of approximation or approximate control part of this application. Okay, so having said all that, you cannot do everything with this approximate controllability. So these Runge type results, they always use they require that the conductivity coefficient gamma is known near the boundary, or it has to be real analytic in some way. So far it has not been possible to use these methods to recover C infinity conductivities, which may have like kind of infinite oscillations near the boundary, or so-called inclusions inside the inclusions. So in order to deal with these cases, there's this other method that I already discussed, complex geometric optic solutions, which are solutions of the conductivity equation, which look like these complex exponentials, harmonic exponentials e to the rho dot x, where rho is a complex vector satisfying rho dot rho equal to 0. And one can think of these solutions also as some kind of localized potential. So these solutions also concentrate energy on some parts of the domain. So actually these solutions are exponentially small when the exponential is decaying. So there's a half space where the real part of rho dot x is negative. But they are also exponentially large in the set where this thing in the exponential is positive. So they blow up in a half space, and they are almost like 0 in another half space. So there are some kind of localized potentials, but unlike in the Runge approximation, these solutions you control in the whole domain. There's no exceptional set like we had before. And these can be used to deal with this C infinity and the low regularity cases as well. Okay, so that concludes the second part of the talk. Any questions? Can you still hear me?
If I may?
Sure.
So here in several places, you seem to use some kind of quantification of approximate controllability. So I guess that the tool you are using at this point is Calderon estimate, or is it something more?
Yes, yes. So you get this quantitative somehow approximate controllability results by duality from quantitative unique continuation results, and the unique continuation results you typically prove by Calderon estimates.
Okay.
So that's correct.
And so this kind of different rates, like epsilon, like Eulerian or logarithmic, well,
Right.
this exponential epsilon to the power minus mu. It is these are the same kind of stability we have for the inverse problem of recovering the data from something in U, or is it
yeah. So some of the
technique, right?
Yes. So some of the motivation for this theorem was that that you could use this this quantitative Runge approximation property to make some earlier results where you show uniqueness in some inverse problems by using Runge approximation, make them quantitative, so prove a stability result for the inverse problem with either some Hölder or logarithmic modulus of continuity. And then these rates here exactly correspond to the kind of stability that you could prove for these inverse problems results.
Okay, thank you.
Okay, yeah, thanks very much. Okay, so if there's no other questions, then maybe I can go to the final part of the talk where we go to fractional equations and see how the approximate controllability becomes more powerful. Right, so now instead of a second order PDs, we are going to study inverse problems which involve the fractional Laplacian minus Laplacian to power s, where s is a number strictly between 0 and 1. And you can define the fractional Laplacian in many ways. And one way to define it is by using the Fourier transform. So minus Laplacian to the s of u is the thing where you take the Fourier transform of u hat, then you multiply it by norm of psi to power 2s, then you take the inverse Fourier transform. And maybe one of the main properties of this operator is that it's non-local. It doesn't preserve support. So for instance, if u is supported in a ball, then the fractional Laplacian of u is not supported in the same ball anymore in general. And also if you want to compute the value of the fractional Laplacian of u at x, then you need to take into account the values of u far away from x. Whereas if s is equal to 1, then in order to compute the Laplacian of u at x, it's enough to know u in a very small neighborhood of x. So it's a non-local operator, and things change because of this. And this comes up in kind of some non-standard diffusion models. So the usual model for diffusion would be the heat equation, which also has this kind of Brownian motion in interpretation. But there are certain so-called anomalous non-standard models of diffusion, which are modeled by different equations. So there's so-called super diffusion, where you have a fractional Laplacian in the space part. And so in probability theory, these would be modeled by Levy flight processes. And you also have subdiffusion, where you have a fractional derivative in time and usual Laplacian in space. So that is related to continuous time random walks. So I'll be interested in the middle case, which is this super diffusion. And this comes up if you have a diffusion process which has some long range interactions, for instance, in some turbulent media, like you think of the atmosphere, or in certain kind of population dynamics models, where somehow the food for a certain species is not distributed evenly, so it is distributed sparsely, and then these animals will sometimes make somehow, they will go a long way in order to find food instead of staying in a small neighborhood. And also in some models of non-local elasticity, these come up. And in probability theorem finance, the fractional ablation is related to Levy processes. So it's actually the infinitesimal generator of the alpha stable Levy process. And so there have been lots of results for the third case, where you have a fractional derivative in time in inverse problems. And then we set out to study the case of space fractional equations. So let me try to formulate the Calderon type problem, which involves this fractional ablation. So again, omega is a bounded domain in Rn, and now you have some potential Q in L infinity of omega. And you want to look at the solutions of the fractional Schrödinger equation minus Laplacian to S plus Q u equal to 0 in omega. But now, because this operator is non-local, it's not enough somehow to prescribe the value of u at the boundary. You actually have to prescribe u in the whole exterior. So this omega e is the complement of omega bar. So this is the exterior domain. So somehow you prescribe exterior Dirichlet data f in the whole exterior. And then if f is in the solar space hs in the exterior, then there is a solution in hs of Rn. And the Dirichlet-Neumann map in this case would be the one which takes the exterior Dirichlet data f into the exterior Neumann data, which in this case, in principle, there are different candidates, but the fractional ablation of u in the exterior is one natural candidate for Neumann data in this non-local setting. This is the work required to maintain Dirichlet data f in the exterior. But formally, this looks the same as the Calderon problem. So you have a Dirichlet-Neumann map lambda q, and from the knowledge of this map, which is somehow exterior boundary measurements, you want to determine the potential q. So the result we got with Gosch and Ullmann was the following. So omega is any bounded set, S is between 0 and 1, and you have two potentials Q1 and Q2. And this is kind of a local data problem. So you are only making measurements in small sets. So you have this blue set W1, and you are imposing your Dirichlet data only in this blue set. The Dirichlet data is going to be 0 outside of W1. And the Neumann data you only measure in this red set W2. So from this exterior Dirichlet-Neumann map, where the Dirichlet data only lives in W1, and you only measure the Neumann data in W2, this could even be disjoint sets. You can show that Q1 is equal to Q2 in omega. So you have uniqueness for the inverse problem. And this is, there are some kind of important differences compared to the classical work in the Calderon problem that I showed in the beginning. So you get this local data result for arbitrary, even possibly disjoint subsets of the boundary. So this local data problem was still open in the Calderon problem in dimension 3 and higher, but in the fractional case, this can be done. There's no difference with respect to the dimension. So the same method works in any dimension. And it's kind of a new mechanism for this non-local inverse problem. Or you can also think of it as an old mechanism. So it's basically the roon approximation property in a new form. And this even works with a single measurement. So you don't have to be able to do infinitely many measurements. You don't need to know the whole map lambda QF, but you can just fix one exterior Dirichlet data F and measure one exterior Neumann data, and that is already enough to determine the potential. Okay, and there has actually been a lot of work on this topic. So the preprint for that result came out many years ago, and there have been many further works. And let me just mention two. You can actually do the low regularity problem. So for potentials, you can basically do optimal regularity in arbitrary dimension. So this was open in the classical Calderon case, at least in high dimensions. And also you can prove a result in the anisotropic case. So the Dirichlet-Neumann for this equation, where now you have a matrix coefficient a of x inside. If this a of x is known, then you can determine q uniquely. So also this matrix coefficient case is not known in the classical Calderon problem. There have been lots of other works. I don't have time to mention all of them. Okay, but then, so maybe it's more interesting to discuss what makes this possible. So there are differences between the fractional and this classical second order equations. So the first difference is this kind of strong uniqueness property for the fractional equation. So there's this theorem that if u is an arbitrary Sobolev function, maybe in some negative Sobolev space, and if there is some open set in Rn, so that both the function u and the fractional Laplacian of u vanish in the same open set, then this function u has to be 0 in Rn. So it's really kind of a, if both u and the fractional Laplacian of u vanish in some open set, then u is identically equal to 0. And of course, this kind of result cannot be true for the Laplacian. For instance, if you take an arbitrary function u in C infinity, C of Rn, then both u and Laplacian of u, of course, vanish outside of the support. Still, this u is non-trivial. So this is a non-local property. It's essentially due to Marcel-Ries. This can be understood as a vanishing theorem for Ries potentials. And you also have some other kind of strong unique continuation results. So let me say a few words about how one proves this kind of theorem. And here's the theorem again. If u is a Sobolev function in Rn, and if both u and the fractional Laplacian of u vanish in some open set W, then u is 0 in all of Rn. And well, there are a couple of proofs, but maybe the most powerful one is related to an extension problem. So you start with the Rn, and then you add one more dimension. Somehow you go to the upper half space in Rn plus 1. And the idea is that this fractional Laplacian of u can be understood as some kind of a Neumann data for a function w which lives in the upper half space. So this w is called the Caffarelli-Silvestri extension of u, and it solves the following problem. So you go into the upper half space Rn cross y bigger than 0, and now you have a second order local equation in the upper half space for this w, and you put Dirichlet data u on the boundary of the upper half space. So somehow u will be the Dirichlet data. You solve the second order elliptic equation in the upper half space, and then the fractional Laplacian of u will be the Neumann data for this w. But you need to put these weights here, and these weights are a little bit tricky because they go to 0 or to infinity at the boundary, but they are still in this Muckenhaupt A2 class, and you can deal with this. You can prove Karlemann estimates for this problem, and then you can show this uniqueness property in this extension problem. So here's a picture. Somehow, so this is the idea of how you prove a kind of quantitative uniqueness theorem, propagation smallness. So you have Rn here, so it's the boundary of the upper half space. You have xn plus 1 going up, and so you have the vanishing of both the Dirichlet data u and the Neumann data fractional Laplacian of u in this set W, this blue set here, and you have your original domain omega, let's say, and you want to show that this u is 0 in omega. So, or you could think that the Dirichlet and Neumann data are small in this set, and you want to show that then the solution has to be 0 in this set as well. So you somehow go little by little. So from the smallness of the Cauchy data here, you show that the solution W has to be small in this half ball. For this, you use some boundary Karlemann estimates. And once you get smallness in this half ball, you can do a chain of balls argument using these 3 balls inequalities to propagate the smallness from here all the way to some point here. But then if you want to go back to Rn, which is the boundary here, these balls have to become very small. Somehow the radius of the ball has to be comparable to the distance to the boundary. So at some point you get lots and lots of balls. So at some height h, then you just stop the argument and then you somehow do some kind of optimization on the number of balls related to the height h and use some Sobolev trace estimates to conclude that the solution also has to be small here. So that's how you would prove this kind of theorem. And then the second main tool is this approximation. So here we can do a comparison to the classical case, the Laplace equation. So solutions of Laplace equal to 0, which are harmonic functions. They are in many ways rigid. For instance, in one dimension, then the Laplace equation is u prime prime equal to 0, which implies that u has to be an affine function. So these are the only harmonic functions in 1D. You also have the maximum principle that the harmonic function cannot have any interior minimum or maximum. And also the unique continuation principle has to hold. So these are constraints that you have for solutions of the Laplace equation. And in terms of approximation, if you have a sequence of harmonic functions which approximate some profile f, then just by taking the Laplacian of the sequence, you get that also this f has to be harmonic. So you can only approximate harmonic functions by harmonic functions. But in contrast, when you go to the non-local case, solutions of the fractional Laplace equation turn out to be very flexible instead of being rigid. So here's the approximation result. So it says that any function f in L2, so this f does not have to be a solution anymore. It can be any L2 function, and it can be approximated, for instance, in the L2 norm by solutions of the fractional Schrödinger equation restricted to this set omega. And even you can confine the support of these global solutions into basically outside omega, there's some small set W. And this extends an earlier result by Di Piero, Savin, and Baldinocci. So really, for this non-local equation, you have a very strong approximation. You can approximate any profile in L2, not just any solution by global solutions. And okay, this kind of approximation property again can be proved by duality from this strong uniqueness property that I just showed. And maybe I'll say that this approximation property extends to many other non-local equations, for instance, the non-local heat equation or the somehow the fractional wave equation and some other equations. And these somehow flexible approximation properties have also been used to obtain control theory results. At least there are many works by Varma and collaborators. There could be many more. Okay, but I guess I'm getting close to the end. So let me maybe just end with a summary. So I was discussing the Runge property, which can be understood as approximate controllability for second order PDE. It allows you to approximate solutions in a subdomain U by global solutions in omega. And in the Calderon problem, you can use it in some special cases, like when the conductivity is known near the boundary or real analytic. But in general, you need complex geometrical optics methods to deal with general coefficients. On the other hand, when you go to the fractional case, this fractional operator is non-local, and these fractional equations may have some strong uniqueness and approximation properties, and this allows you to get better results, for instance, in inverse problems than you can do in the classical case. Okay, but let me stop here. Thanks very much.
Thank you very much, Mikko, for this interesting talk. I don't know if anyone has a question or comment. I can start. Just a small question, Mikko. The Dirichlet-Neumann operator of this of the equation with the fractional operator corresponds with the usual Dirichlet-Neumann map. I mean, the Neumann value is the fractional Laplacian. This is not to the power s. When,
yes.
So the usual Dirichlet-Neumann map. This is the normal derivative, no?
That's right. So there are different analogues of this classical normal derivative in the non-local case. But so we looked at the few candidates which appear in the literature, and they seem to be equivalent actually to this one. And this you can make some physical interpretations of this quantity, which somehow justify calling it somehow the Neumann data in this fractional case.
Okay, because I will say that from a first point of view, the s equal to 1.5 no will be natural in order to correspond more or less with the normal derivative.
That's true. So if s is equal to 1/2, you have this connection that actually minus Laplacian to the 1/2 is actually the Dirichlet-Neumann map of the upper half space. You are right.
So okay,
And
so I wonder if
somehow...
Sorry.
Yes.
I wonder if this difference makes these different properties arise. Well, I don't know.
Yeah. So certainly the non-locality is one thing, but also that you have this Caffarelli-Silvestri extension property that these fractional operators can be understood as the Neumann data for some second-order PD which lives in the upper half space. So that is very helpful.
Yeah. Okay. Well, thank you very much, Mikko. There is some questions. Pei Su, maybe you can start.
So, can you hear me?
Yes.
I want to ask you a simple question about the definition about this fractional Laplacian.
Yes.
The slides is divided by Fourier transform.
Yes.
I see another definition, which is integral definition. It's a principal integral.
Yes.
So it's as equivalent.
Yes, they are equivalent. So
always use a definition for this, which is divided by a series, a Fourier series. I use associated with diagonalizable operator.
yes.
This is I usually use. So as there are some difference between this definition.
Yeah, so there's a difference if you are looking at this non-local operator in all of Rn compared to if you are looking at the fractional operation in some domain. So in Rn, there are many equivalent definitions, and I think in Rn it's quite canonical, like what should be the fractional operation. So there's a paper called 10 equivalent definitions of the fractional operation in Rn. So there's really many. But if you go to some domain omega in Rn and you try to define some kind of fractional operation in a domain, then there will be many definitions and they are not all equivalent. So then it starts to depend on your somehow problem. What is the best operator for your problem? Yeah, but that's true.
This integral definition appeared in the article by Worma. You mentioned in the slides.
Yes, but it's actually equivalent to this Fourier transform definition. I think he uses these operators in Rn.
So the definition I used is Fourier series. It included the boundary condition inside. So maybe,
right.
Okay. Thank you for your interesting talk.
Yeah, thanks very much.
Thank you. There is other questions. Kevin?
Yes, thank you. I have a question concerning the first part of the talk, concerning the open problems related to Calderon problem. So yes, the third problem. So is there a link with the counterexample that is given by Poisson to unique continuation for elliptic equation or not?
Yes, actually there is a recent paper. It's a very interesting paper by Daudet, Cameron, and Nicolau, and they do exactly that. They show that for this Calderon problem with local data, so they give an example of a domain, and I think for them it's a manifold, and so that a subset gamma, which is part of the boundary of that manifold, and they give somehow kind of two matrix conductivities, which are related to this counterexample by Poisson and Miller, so that they also get the counterexample to the Calderon problem with local data for matrix conductivities. So that is known. So and that's actually a kind of very nice result that shows that you can, in some cases, convert the counterexample to unique continuation into a counterexample for the Calderon problem. And these coefficients, they are C alpha with alpha less than 1, like in this Poisson and Miller counterexamples. Yeah, but that's a good question.
Okay, thank you. And I have also another question. It was concerning the second part of the talk. When you prove approximate controllability result in some sense for elliptic equation, can you give some estimate on the control in function of the coefficient, for instance, that, yes, I don't know if you can go to the second part, perhaps it would be more clear. Yes, for the, no, just before, if it is possible. Yes, here
This
for
one.
instance. Yes, this one is good. So for instance, can you give some estimate of the function f in function of v on the coefficient of p or not?
Right. So you're asking an estimate for this f, the boundary control, and the size of that. But actually, for this equation, if you have p u epsilon equal to 0 with Dirichlet data f, then the h1 half norm of f is comparable to the h1 norm of the solution u epsilon. And our result with Ryland gives estimates for the h1 norm of this u epsilon.
Okay.
So that this gives the similar estimate for the h1 half norm of the boundary function f.
Okay. Yes. Thank you very much. Thank you.
Yeah, thanks.
Silvan also have a question, maybe?
So if I may, again, so well,
sure.
Thank you, Mikko, for this very nice talk. I was also wondering if you got some stability estimates for the uniqueness in the Calderon problem with fractional operators, and if so, how does it depend on S? I guess that when S goes to 1, it has to blow up very strongly, no? Yeah,
so that's another interesting question. So we have this somehow different method in the fractional case, and we were wondering if you might also get better stability, but it turns out that you don't. So for any S between 0 and 1, you can prove that somehow the unknown coefficient Q depends logarithmically. So there's a logarithmic modulus of stability involving the Dirichlet-Neumann map, and that is optimal. So it's somehow, yeah. So and you can do that by doing everything in the proof quantitative. So we use this approximate controllability somehow. So you can think that if you have a quantitative approximate controllability result, which you can get by if you have a quantitative uniqueness result, which we actually did with Ryland by using this. So there was this picture like doing one. If the Cauchy data is small here, then we propagate the smallness to say that the function also has to be small here. Yeah, so the stability is actually for any fixed s between 0 and 1, it is only logarithmic. And I actually don't know how the constants behave when s goes to 1, but it's still going to be logarithmic when s goes to 1.
But you said that you only need one measurement, right?
Yes, that's true. So
in
some sense,
the
we use
limit,
much.
the formal limit s goes to 1, at the end you need the whole Dirichlet to Neumann map, no? Or some partial data, but okay. Still.
Yes. So there's kind of another difference in the fractional case. So in the fractional case, you are measuring in open sets. So these are somehow n-dimensional sets. Yes. Whereas in the classical case, you are only measuring on the boundary, which is n-1 dimensional. So somehow in this fractional case, if you formulate it like this, your measurement depends on, it has more degrees of freedom than in the classical case. So that's why it's possible to do this non-local problem for only one measurement, whereas in the classical Calderon problem, it's impossible with only one measurement.
Okay.
That's another difference between the two. And it is an interesting question, like whether you could somehow take the limit when s goes to 1 and recover some result in the classical Calderon problem in this way. But so far, this has not been possible. It seems that there's some kind of phase transition when s goes to 1, so it's not easy to get some results in the classical case from the fractional ones.
And maybe some last question. So is there a way to choose the f, the best f in some sense, to get the best stability in the inverse problem? Does that make sense?
Yeah, that's a good question, and we don't know. That's something which I think is not understood. So we only know something about this cost of approximation, but we don't know like how to find the, let's say, the optimal f in some sense, what the optimal f should look like. So that would be an interesting thing to understand, but we don't know at the moment.
Okay, thank you very much.
Yeah, thanks.
Okay, thank you, Mikko. If there is no more questions, so we thank you again, Mikko, for this very interesting talk. There is another comment? No? Okay, well, thank you very much, Mikko, for this.
Yeah, thanks very much for listening. It's been a great pleasure.
Thank you very much.